right? Okay. Let us consider how can we control a model, how can you use a model to control a robot. Let us start with a general case. It's true for any kind of robot, not just a manipulator. So let us assume that we have a model for acceleration. Model is ordinary differential equation, second term, type of second order. So acceleration equal to the some term that does not relate to our input. U is input, so F1 plus F2 times input U. Okay. If we consider a fully actuated model, fully actuated system, we can choose such U that looks like this. Why? Because we can put it inside our dynamic model, and what will we get? So this is the thing, right? So F2 times F2 negative will equal to the identity matrix, right? And it will be F1 minus F1. So we will left just with the U prime. Can you see it? Pretty simple. And it means that our actual acceleration will be exactly as our additional input U prime. And it means that our system will, we can control our system in arbitrary direction. We can get any kind of motion within workspace. For example, if we have this kind of model, M, Q, Q double dot plus C plus M equal to U, we can rewrite it in a way as you can see here. And this will be F1, this will be F2. And it only can be done for fully actuated system, because only for fully actuated system you can compute M inverse. If it's under actuated system, you cannot do this, because it will not be full rank. So this is F1 and F2, right? So for fully actuated system, we can do the same trick. So we can choose this kind of control. So it is the ordinary general case. Let me choose another color. And we can substitute in our model. And as you can see here, we will left with just Q double dot equal to the U prime. Instead of U prime, we can choose any control law, for example, like this. It looks like PD control. KP right here. Let me choose another color. KP is a proportional coefficients. QD is a desired. QA is actual position. So this is the time derivative of the desired and actual position. KV is proportional coefficient to the D, so it's like PD control. But also we can send here the desired acceleration. But actually we can choose here whatever we want. And our robot will follow this trajectory. Finally, this is the equation that we need to use in order to compute torque, which need to be applied directly to the robot joints. Just like here, in previous example, we use this PID plus E component. Right now, we can use this model. And, for example, if your system will, you can choose, if you want to choose mass, length, or any other kind of parameters of your system, you can adjust your just model, and that's it. KV and KP will be the same. Or you need to tune it just a little bit. In this case, you need to choose different kind of coefficients each time when you change the system. Let us take a look at an example. So right here, I have a model. Model-based control. So you can see that it's also capable of doing the same trajectory. So animation looks pretty much the same. The motion is the same. But here you can see that I do not use any PID control. I'm sending computed taus into the system. Tau is computed here in MATLAB function. And if we'll go inside, you will see nothing else as just our components M, CQ, and N. Can you see it? You can see here also U, which is our additional control. And U is computed in additional model, function. And right here you can see the equation. I cannot unscroll it for some reason. Okay, but you can see the equation, right? It's just too big. Desired acceleration, kV, the difference between desired velocity and actual velocity. This is. And right here is the difference between the desired position and actual position. So and it just works. So all others plots will be pretty much the same. So this is the difference between actual and desired trajectories. And you can see how our robot goes from initial position to the desired one. So you can see it for the P, you can see for the Qs. Actually, you can see that the difference is lesser because our system already knows the whole dynamics of our robot. Only two components that we need to tune is the KV and KP. And just look. Previously, in previous example, I found the coefficients manually without any consideration of dynamics and without any analytical tools, and you can see how big those coefficients are. So I started with 1 and I increased them until I was happy with the result. And you can just think how much time I spent to tune it. But for the dynamics, you can see how small coefficients are. It just was like second guess. So I do not need to tune a lot those coefficients, since our system already knows the dynamics of a robot. And it's much easier to find the optimal coefficients and to create the efficient system. Is it clear now? Okay, you will have those models. I will send it to you, so you will have pretty much time to consider the examples. So right here, I just explained you the idea. Please take your time to consider the models. Okay.